All right then. So I think it's just gone 2 o'clock, and we can kick things off. So yeah, it's a great pleasure to welcome this week Roberto Cerbino from the University of Vienna. It sounds like Roberto's just joined the physics faculty in Vienna in 2021 after time in France and Milan, and lots of exciting positions in both biological modeling and in physics. So yeah, we're excited to hear about this DDM method that people in Cardiff have also been using. So very fitting, and also this is our last talk of the season, and so yeah, it's a nice way to end things. So away to you, Roberto.
Thank you so much, Thomas, for the kind words and for the invitation to this seminar. And I was saying before the arrival of most of the people here that I'm a physicist, so I'm a bit afraid to give a talk in a framework where there are a lot of mathematicians, and I will try to not say anything that will be used against me in court at a later time. But if I happen to do, please be merciful. And with this disclaimer, I had prepared a little bit of an introduction very quickly about who I am, just to give you an idea about my career. So I started my academic career in Milan, where I did my PhD in physics and my first postdoc with Marzio Giglio. And everything I know about optics, I know to Marzio. I owe it to Marzio, because he was the one who introduced me to optics as an experimental science. Then I moved to Fribourg with a Marie Curie fellowship to work with Frank Scheffel. And while with Marzio, I was working mostly on single scattering and traditional optics. With Frank, I got involved mostly in multiple scattering and glassy systems. Then I moved to Milan, back to Milan, but not any longer in the physics faculty, in the medicine faculty, which in Milan is a very big faculty. Just to give you an idea, the Milan University has 2,000 professors, 700 of which are in the medicine faculty, which is more than 1/3 of the teaching bodies. And then I gradually started to get interested in biological and medically relevant problems. And for this reason, I also moved as a visiting researcher first to Ottawa in Canada, where I collaborated with Jim Harden, this guy on the right, and Andrew Pelling. And Andrew is a quite famous TED fellow who loves to grow parts of the human body, or at least things that have the shape of parts of the human body from apples, which is a kind of interesting occupation. Then I moved to Lyon, where I spent a month as a visiting professor hosted by Sergio Ciliberto in the framework of the hosting program they have in the summer. And then in 2021, I finally moved to Vienna, where I have my new group, and slowly with COVID and everything is getting more and more populated. But if you happen to be in Vienna, you're more than welcome to come over for a coffee. And you know that coffee has been brought by Turkish people when they were sieging Vienna. And apparently here in Vienna, I was not aware of that because I'm Italian. We think we have the best coffee in the world. But apparently here in Vienna, there is also good competition in that respect. Now, my research is a kind of multidisciplinary, and I made this cloud of words with all the words that appear in the abstract of my papers, which are in archive. Not all of them, but are the most recent. And you can see that I do a lot of dynamics, and this is the main topic of today's talk. But I do it on different systems. I do it on cells. I do it on colloidal particles. I study diffusion, and this is a pretty good representation of my activity. And you see that DDM, which is the main topic of today's talk, is a big word, which means there happens a lot of time to be present in my abstracts. So in all the things I do, I would say that light and image analysis are the glue. And to show you a little bit what I mean, these are movies or say videos that are extracted from publications. Some of the publications I've been involved with. And you can see that You can see things that range from pattern formation in convective liquids to Brownian motion in colloidal suspensions, to the embryo of Drosophila, to bacteria moving in a very dense environment, to biosensors detecting ligands in a complex fluid, or endothelial cells, epithelial cells. These are nuclei that are photo-damaged, and then we look at how the repair construct go where they are needed to repair the DNA. And also, for instance, this is a work I'm very proud of. In this work, we studied the kinematics of the jet emitted by these fish, which are called archerfish, which are very, very good predators who dislodge their prey by emitting a very powerful jet of water. So all these images have been acquired in direct space. So you see a real space representation of the system of interest. And this is actually something that has been increasingly used in modern times because people love to see things in direct space. So, but if I have to say, if you ask at least in the framework of soft matter physics, which is what I do, who likes direct space versus, oh, sorry, there is a mistake here. This real is supposed to be reciprocal. I apologize for that. So who likes direct space and who likes, in contrast, reciprocal space, you'll find good arguments for each one of them. So for instance, in direct space, and this is a very nice super resolution microscopy image of a red blood cell. So the scale here is 1 micron and the scale bar. And you can immediately see that with direct space imaging, now with super resolution microscopy, we are pushing it at the limits of the knowledge. So we can see inside the cell what's going on. And this allows us to basically be able to investigate heterogeneity within a cell. So regions where, for instance, something is occurring and something is not occurring, or at the same time, if we're interested in the dynamics of the system, we have to pay a price. The price that we have to pay is that all these techniques in microscopy and direct space are not that fast, because to collect an image, we need to fill the pixels of a pixelated detector, and this takes time. And the second main disadvantage that we have is that statistics is usually not so rich. What do I mean by that? Is that whenever we want to do a lot of statistics, there is a trade-off between imaging a large number of individual objects and having a large resolution. I chose specifically this image because this is one of the cases in which this trade-off is pretty advantageous, because we still can count a large number of individual green dots, which, by the way, in this particular case are spectrin, fluorescently tagged spectrin proteins, molecules. And but this is not a normal situation. So if you want to zoom in, very often you have to pay a price, and the price is that you are collecting signal from a small number of objects. So while this is often not true for samples like this one, which have been fixed, and in this case you can do what you want, you can stitch different images, you can do a lot of things to bypass this limitation. If your sample is dynamic, well, this trade-off becomes even more difficult to manage. In reciprocal space, we can see very small things. And I mean, this is a very famous example. This is the first picture of DNA in reciprocal space taken by Rosalind Franklin, who was able to crystallize DNA and to get from this repeated sequence of DNA molecules a photograph of the sample, which is not a direct space photo, is a reciprocal space image. For this reason, because we are not necessarily interested in resolving the individual objects, but we are more interested in getting an information about the statistics of repeated statistics of the individual units. Well, we are able to go well below the resolution of the technique. And the resolution when we deal with radiation is typically given by a fraction of the wavelength. So if we use light, we cannot go with normal classical techniques, we can not go too much smaller than 200, 300 nanometers. While if we use X-rays, like in this case, this is an X-ray diffraction pattern, we can go at the nanometer and below scale. Now, there is not only disadvantage, is that because of the fact that we are illuminating a large region of sample in which there are several of these elementary units, we get a lot of statistical information about our sample, which is something that in real space is not easy to get. And because we can also do this dynamically nowadays with detectors that sit down at one point in this diffraction pattern and monitor the time evolution, we can catch very fast dynamics. It's not uncommon to see dynamics down to the nanoseconds and even below. The price we have to pay, of course, is that we don't have resolution in space. There is no way we can know if our illuminated region is heterogeneous, for instance, is made of objects that do one thing in one part and another thing in another part. And also, it is not so easy to discriminate different subspecies. So if we have, for instance, two types of DNA, it's not so easy to discriminate between the two of them by looking at these diffraction patterns, unless we have a good model for the two of them. Now, if we now restrict our attention to light, typical light scattering experiments are performed in two different configurations. In the first configuration, which is this one, I hope you see my mouse, you have light which is sent normally in the form of a plane wave onto your sample, and then this very well-defined directional beam is producing scattered light all around the sample. Now, if you go in a particular direction, very far away from the sample, and you collect this light, you are basically probing a Fourier component of the density distribution within your sample. Now, the same result can be obtained by going very close to the sample. And in this case, what you do is you place a lens and you form an image of this Fourier plane. So there is a first lens, and in this plane here, you can show that you have the Fourier transform of the refractive index distribution of your sample. Now, this Fourier transform is normally imaged by a second lens on a CCD detector, and these experiments are completely equivalent. So in the language of Fourier optics, in this experiment here, the one on the top, you send a plane wave and you go so far away from the sample that you can decompose the scattered light from your sample into plane waves propagating in different directions. And so this idea that now positions far away from the sample do not correspond to position, but to correspond to angles is actually the key idea behind the Fourier transformation. And of course, in the second configuration, you have something similar, because now you can show that plane waves arriving on the lens are now focalized into points into the detector. And again, this is the physical realization of this mathematical beauty, which is the Fourier transform. Now, in this framework, the main question I want to answer in this talk is if there is any alternative to this very classical way of getting scattering information. And the answer I want to give is yes. And you can read more about this idea, which we name digital Fourier microscopy, in this review paper that I wrote together with my colleague Fabio Giavazzi. And the main idea of this paper is that you can replace physical propagation in the far field or lens-assisted propagation, which are the two configurations I just described 2 minutes ago, by digital propagation, which means making use of Fourier transforms of images rather than letting the Fourier transform occur physically by light propagation in real space. Now, the take-home message, if you fall asleep in the rest of this talk, is this. You can collect a temporal sequence of images, which we call normally a video, movie. And you do that in direct space. So you acquire videos such as the ones that I was showing here. All the data we will be talking about, forget about the fish and the biosensor, all the other videos here can be used to do exactly what I will be talking about today. You take videos like this, so you have videos in real space of your samples. And now you could do, of course, a lot of things with this video. For instance, in this video here, you could do tracking. You could take your colloidal particles and track their position as a function of time. But in this video here, you cannot do tracking. In this video here, you cannot do tracking because what you see is below the resolution of the microscope. The same is true also for this embryo here. It's impossible to do tracking in these experiments. So now, my claim is that if you take these videos in real space and you analyze them with a spatial Fourier transform-based analysis, well, under suitable condition, the information that you can extract is equivalent to the one that you would extract in the two scattering configurations that I showed you in the previous slides. Now, what is behind this idea? Behind this idea, there is a sort of generalization of the fact that we all know that if we take a function in one dimension, we can write this function as a sum of sinusoidal components. This sum is a series if this function is periodic, and is an integral if this function is non-periodic. But we know from Fourier that this is possible. If we look at what this means for images, it means that this image of Monsieur Fourier can be Fourier decomposed into the equivalent of this sinusoidal modulation, which are these two-dimensional sinusoidal modulation that you see in this lower row. Now, if you think of one of these modulations, if you take let's say, a cut of Fourier phase and you still obtain a one-dimensional representation of Monsieur Fourier, well, what happens here is that you can imagine that this image can be written as the average value plus the Fourier components, the first harmonic, the second harmonic, the third harmonic, and so on. I'm still in the framework where I imagine this to be a series, but of course you can imagine that this can be easily generalizable to the integral. Now, if you send a plane wave onto this guy, the DC of the signal, well, what happens is that you reconstruct your transmitted beam. So your lens here, you take a lens, and the plane wave sends this a plane wave propagating along the optical axis will be focused in the Fourier plane onto this point. Now, if you take the first harmonic, so the fundamental, this acts as a sinusoidal grating. And in optics, we know that these sinusoidal gratings, they are illuminated with a plane wave, and they create two plane waves propagating with an angle, which is the same with respect to the optical axis, which means that once they are focused in the Fourier plane, they are basically 2 points at the same distance from the axis here. Now, if you increase the frequency of this sinusoidal function, this lens will always send this signal onto 2 spots, but this time the 2 spots are actually further away from the optical axis. So we have a perfect way now to associate our Fourier components of the image to gratings, and this grating to something that sends our signal onto distinct but controlled positions in the Fourier plane of our lens. Now, if you remember that in the Fourier plane of this lens, what we get is basically the scattering pattern, it means that the scattering pattern that we measure is nothing else than the Fourier decomposition of my original refractive index distribution. Now, this last case is just to show you that when this frequency becomes too large, the 2 plane waves do not enter the lens, which is another way to associate the fact that a lens, the lens size, so the numerical aperture, is also responsible for the resolution of the optical system, because if the lens becomes too small, then of course you wouldn't be able to detect the corresponding frequency modulations whose frequency is large enough to miss the lens entrance aperture in the very first place. Now, this is basically a justification of one of the geometries that I showed you. But why we can use this to do some quantitative microscopy? I mean, this is not something that was discovered by us. It's something that was discovered essentially by Abbe. And Abbe came out in the 19th century with a very elegant theory of image formation. So what Abbe said is that if you take our image and one of the Fourier component of the Fourier components of our original image, well, this one will give rise to, let's say, if you take this, the DC value and the first harmonic, what happens is that the DC value will give you in the Fourier plane this spot, and the first harmonic will give you these two spots. So far, so good, nothing new. But what Abbe said is that in the focal plane of the lens, you get this. But then if this lens is forming an image of this plane onto this other plane, what happens is that from here to here, you get a Fourier transform. And from here to here, you get an anti-Fourier transform, an inverse Fourier transform. So based on Abbe's interpretation of imaging, imaging is nothing else than a Fourier transform followed by an anti-Fourier transform. Now, the starting point of my talk is that given that we know that this gives rise to the image of the object, possibly filtered because the lens misses some of the frequencies that escape the lens because of the finite size of the lens, and this is the so-called point spread function of the optical lens. But apart from this, the most important thing is that there is a one-to-one relationship between the Fourier components of the image and the Fourier component of the object. So the starting point of our reasoning is that you don't need to go here and record the Fourier transform, because you basically can calculate the Fourier transform on your images. So now that I hope I convinced you that there is a one-to-one relationship not only between the image and the object, because this is at the very core of imaging, but there is also a one-to-one correspondence between the Fourier components of the images and the Fourier components of the object. So this grating is the same of this grating, possibly magnified, but this is something that we can take under control. Now, the second ingredient we need to understand is that given that this guy, this frequency, determines this angle, well, when I decompose this original image in frequencies, I basically also measure this angle. But it turns out that this angle is the so-called scattering angle, which is the difference between the incident wave vector and the scattered wave vector. And this wave vector, sorry about it. So I think there is a problem here. I don't know who that was, but I think I apologize. I hope they don't call back. In case they call back, I will. So I hope this does not happen again. My apologies for this. So basically what happens here is that this small wave vector here, which is the difference between this incident vector and the scattered vector, is actually also very important in scattering experiment. This is called the scattering wave vector. And this gives you an idea of the momentum that has been transferred during the scattered process, and is mainly responsible of the fact that your light has been deviated from the original direction. So if you now go back to our experiment, you have a scattering grating here. You can interpret this scattering from the grating in the same way. And so if you now take your object and you decompose it into Fourier component, each Fourier component of the object will cause scattering at a different angle and will cause scattering at a different wave vectors. Well, the good news is that when you Fourier decompose your signal of the image, you have the same mapping. Now, how can we make this more formal from a mathematical point of view? Well, first of all, we need to define a generalized density of my sample. So my sample could be, for instance, a binary fluid in which there is a concentration of species 1 in species 2. And for instance, this could be ethanol in water, or could be, I don't know, colloidal particles in water, and so on and so on. Or could be a more complex object, like, for instance, the director that defines the orientation of a nematic phase in a liquid crystal, which fluctuates because of thermal fluctuations. Whatever this is, I mean, let's call it a generalized density. For the sake of simplicity, let's imagine that this generalized density today describes a set of n colloidal particles that are placed in position xn, and whose position is identified by a delta function for each particle, and then the sum of delta function is basically my generalized density. And I just tell you that this is a simplification and generalization without, so without losses, generalization can be done for an arbitrarily complex generalized density. Let's focus for the sake of simplicity on this set of discrete particles. Now, if I have a set of discrete particles in this plane, which is the object plane, imaging is a box that transforms this thing into an intensity. Now, in this paper that I mentioned earlier, this paper about digital Fourier microscopy, you find this described in all details. But the most important thing for what I will be telling you today to be automatically true is that whenever the intensity on your detector can be written as an average value plus a double integral that involves my generalized density, my generalized concentration, and this function here, which is called the generalized 3-point spread function of my imaging system, everything I will be telling you today is true. I'm not saying that when this is violated, everything I will be telling you today automatically doesn't work, but you have to exert more caution in treating the data. So in other words, this equation, which defines linear space invariant imaging, why linear? Because you sum up the contribution of all the particles first by convolving in this plane, xy plane, and then by integrating in the z plane across the thickness of your sample. Everything that can be written in this way, so linear for this reason, and space invariant because if I move my object in this plane, this function remains the same. So the imaging properties do not depend on where the object is located in this plane. So if this is true, we are safe because Fourier transforming this thing will give us the result we want. And what is the result we want? The result we want is a characterization of this C. But we want to obtain the characterization of this C, the generalized density, so the dynamics of the density of the sample. We want to learn something about it by studying the dynamics of the intensity. And so, in principle, you could tell me, well, I mean, why do you want to go in the Fourier space? Because in principle, you can take your image here, sit down at one point, and calculate a temporal correlation. And this, I mean, it makes sense. This is what people would do, for instance, in Fourier space in propagation. Why don't we do the same thing in that space? Because we can surely learn something about it. And the answer is that people have done this. This is called dynamic scattering microscopy, and is described in these two papers. And if you look at the results obtained by these colleagues, it doesn't work. So it works only decently. Let's say they are out by about a factor of 2 for small particles, but not so much for large particles, where there is a difference between the experimental and the theoretical diffusion coefficient, which is more than 1. It's about 1 order of magnitude. So why the hell this does not work? Well, we know it already. Why it doesn't work? Because there is a convolution here, and this convolution operation tells you that you are mixing in one point of the image, you are mixing signal that comes from different angles from your sample. And so because different angles have different wave vectors, and the dynamics of the system, as I'm going to show you in a second, depends on the wave vector, well, it means that you are not probing the dynamics of the different modes of the system, but you are mixing all the modes. And given that the modes relax with a different temporal constant, well, you are basically creating a melting pot of dynamics in which it's very difficult to find the information you're interested in. Can you cure this configuration in such a way that this works? Well, this has been done by Duri, Cipelletti, and collaborators. But in this case, what they do is basically to take an image of your sample, and instead of doing the temporal correlation on the pixels, as in the previous work that I just showed you, what they do is in the focal plane, they put an annular aperture, whose purpose is to select one single wave vector, so one single angle. So they collect light only from one single angle coming from the sample. And in this case, this works because this angle has a dynamics which is well defined because it corresponds to one single Fourier mode of our sample. Now, we know the solution to this problem because we know that the convolution theorem of Fourier analysis tells us that if we take this intensity and we Fourier transform it, this constant goes to a delta contribution, which is not relevant for us, but this convolution goes to a product. And now the relaxation of the modes of the concentration are actually probed by analyzing the relaxation of the modes of the intensity. The only thing that we have to take into account is that their amplitude of the modes is affected by the transfer function, but not so much the dynamics. So this is a crucial result because this result is the one that allows you to claim that the Fourier analysis of the images gives you information about the Fourier analysis of the Fourier modes of the sample. Now, I think at this point is a good moment for me where to stop and ask you if you have any questions, because I will continue from here, but I need you to be with me so far, because if you're not, then it's going to be difficult for me to continue on the talk. So please let me know if everything is okay, if you need clarifications about this, if I failed in conveying everything so far, and so on and so on. So I see a thumbs up from Thomas, Timothy. Okay, so I don't see any complaints, so I will continue. In case you have any questions that you want to ask me later, please let me know. Now, the first question you may ask is, well, this is a very appears to be a very particular way of writing the intensity. How can you be sure that the intensity in a realistic microscopy experiment can be really written this way? Well, I show you, without demonstrating it, I show you all the cases in which this works. The first one is fluorescence-based imaging. Now, in physics, in optics, there are two classes of imaging-based process. The first one is fluorescence, and the main idea behind fluorescence microscopy is that all the fluorophores in your sample, which are these molecules emitting fluorescent light when they are illuminating with another wavelength, they emit light independently. So for this reason, each particle emits light independently, and the intensity is the sum of all the contributions from the particle. So this very simple idea makes this equation to be valid by definition, because this is basically a sum of all the intensity contribution from the particle. The only thing that we need to take into account is the point spread function of the imaging system, which is a well-known fact to all people doing microscopy. So we can use this idea in wide field microscopy, in confocal, and in light sheet, just to name three very popular microscopy techniques. The second case, which is a little bit less obvious, is the case in which imaging is not any longer based on fluorescence, it's based on scattering. So I illuminate my sample with light, and then this light is scattered, and I collect the superposition between the transmitted beam and the scattered light. So this is a very key point, because in normal scattering experiment, what you do is you illuminate your sample, you go far away, and the main definition of far field is that you go so far away that the transmitted beam is completely decoupled from the scattered light. So when you go on your detector, each point you select, it's only scattered light. So you never get the superposition between the transmitted beam and the scattered light. So this is the definition of being in the far field. Now, what we do is we are inside the transmitted beam. And inside the transmitted beam, we collect images whose feature is the following. We have a very bright transmitted beam, on top of which there is a very tiny modulation coming from our signal. So, given that our detectors are sensitive to intensity, and intensity is the square of the field, it is possible to show that to the first order of approximation, there is a very bright contribution due to the transmitted beam, which is not interesting because it's not dynamic. And then there is a fluctuating part, which will change in our movies because of the particles moving around. And this is proportional to the real part of the electric field, of the scattered electric field. Well, because of this proportionality between the intensity and the real part of the electric field, it is possible to show that in this case too, even if it is scattering based, and even if in principle I have to take into account all the interference effects, this equation is still valid. Now, this is a very important claim because it allows us to work with videos of this kind. If you watch this video very carefully, I don't know how well the video will show by broadcasting it through Zoom, but you should see a lot of static spots like this. And these are actually spots that are due to the fact that your collection optics, your cell in which the sample is confined, is actually dirty. So if you have ever used light scattering with a sample like this, you will not get any result because all these dust particles on the optical surfaces will ruin your signal and will create a lot of what is called stray light that will basically make your scattering measurements very difficult to perform. Now, at least at small scattering angles. Now, what is in this movie is a collection of particles whose size is of the order of 70 nanometers. And in this particular movie, the magnification is 40 times, and the pixel size after magnification is 600 nanometers. So there are at least two reasons why we cannot see these particles. The first one is the diffraction limit. So these particles are at least 3 or 4 times smaller than the resolution of the microscope. Let's put it in this way, that the best resolution of a microscope, even more times smaller than the resolution of this particular microscope in this configuration. And then the pixel is roughly 9 times larger than the particles. So there is no way we can resolve the individual particles. But if you are lucky enough to see something in this movie moving, you see that there is dynamics. And these dynamics can be brought to light by this analysis, which can be performed in 2 ways. The first one is to take Fourier transforms of the images. So you take all the images in your video, you take a Fourier transform of an image at time t, you take a Fourier transform of an image at time t plus delta t, and then after complex conjugation, you multiply the 2 images and you repeat this for different delta t's. So this is a so-called correlation function. And if you do this kind of analysis, your signal will have a delta contribution at the origin due to noise, this B factor here. But then there is a decay from a maximum to a minimum. And this minimum C is basically due to these static structures that were due to the defects in my image. So I have a very strong contribution due to the fact that the non-fluctuating part of my images is actually Fourier transformed together with the rest. The interesting part is this, and this A is basically the scattering. So this B is the camera noise, as I anticipated to you earlier. And then this A is basically a product between the scattering profile of the particles and the transfer function of the microscope. The quantity we are normally interested in is this intermediate scattering function, which for those of you who know dynamic light scattering is the same output that we will get in the dynamic light scattering experiment. For those of you who do not know what this is, this function has a decay which tells you something about the way the particles move in your system. This thing is a pain in the neck because it can dominate the signal, especially in cases where this thing is not super static, could be a real problem. So there is another way to analyze these movies. And this way can become more apparent if you take differences between, so in the movie on the right, what we show now is the difference between two images at a fixed time delay. And now we run through the entire movie by keeping the delay fixed. And you see that there is a lot of signal coming from the particles moving, and all the signal coming from the non-moving things is gone. So based on this idea, you can perform a second type of analysis that was originally proposed by these colleagues in these two papers. And this is the so-called Fourier image structure function, in which instead of taking the Fourier transform of the images and then multiply them, what you do is you take the Fourier transform of the two images at 2 times, you subtract them, and then you calculate the amplitude square. So what is called the Fourier power spectrum of the image difference. Now, this function can be proven to be substantially equivalent to the previous one, but the signal, the results, the information about the system is encoded in a different way. The noise of the camera is now appearing as a plateau here, and the signal of interest is now appearing as an evolution from a minimum to a maximum, which is still due to the scattering from the sample. But the important thing is that the signal from the noise, from this static noise on the images is now gone. So there is no trace of the static, very disturbing thing. So analysis based on this is not new in physics. This was also performed in the dynamic light scattering experiment, but it was not used that much in the past beyond these two original publications. And it's proven to be a particularly robust way of analyzing dynamic data, especially when there are very large signals, like in our experiment, or when there is a sort of drift in your signal that mathematically will lead the correlation function to be not defined, but the structure function remains well defined also in the presence of a drift in your original signal. Now, analysis based on this is what is known under the name of differential dynamic microscopy. And this was demonstrated in 2008. Since then, it has been used in a lot of applications. And the ingredients for this to work are very simple: a sample, an imaging device, a camera, a computer, and someone who can use a computer. If you put this in a blender, you find exactly what is known as DDM. And the main principles of DDM were described to you in the previous minutes. And what is interesting here is that this was originally demonstrated in a white light microscope. It gives you Q-dependent dynamics in one shot. And it was used to measure colloidal suspension, whether or not the particles could be or could not be resolved individually. What does it mean, this? It means that you don't need, I mean, if the particles can be resolved, you can do tracking, you can do what you want, but you can still do this analysis. When the particles cannot be resolved and tracking cannot be performed, this analysis still works. Now, in the last minutes I have, because I was particularly slow, I will just try to give you a more detailed flavor of how this works. So if you take a movie and you extract the frames that are labeled by 1, 4, 31, and 301 in this example, which means a delta t distance, 4 delta t distance, 31 delta t distance, where delta t is the image acquisition temporal period, then you can take the difference between these different images by keeping the first fixed and running through the others. And you see that the signal now increases. In the previous movies, I kept delta t fixed and I ran through the movie. And this would give me the same result, but changing because same amplitude, but it's changing because the particle moved. What I have here is a little bit more interesting because it shows you that the particles move more and more as time goes on. So this information in real space is useless, but if we go through a space, we know exactly that is not. And this is the Fourier power spectrum of the differences. We sit at one particular wave vector, and what we find is that we can measure this signal as a function of the time delay. And for these three images, you see that this increases as expected because the Parsifal theorem tells you that the energy, so the variance of the signal in real space and the variance of the signal in Fourier space have to be the same. So it's not surprising that this is true also at the level of the single modes, Fourier modes. Now, interestingly, you can do this also for all the other delta t's that I didn't show in this sketch. And you can fit this with the function I showed you earlier. And so from this fit, you can extract exactly the intermediate scattering function, this object here. Now, if you have a model for this, and in particular for these particles, the model is an exponential relaxation, you can determine the characteristic time of this decay for all these wave vectors. So not only for one wave vector, you fit this and you find the time, characteristic time, you do that for all the possible wave vectors in this image. And in this particular example, the image is azimutally symmetric, so you can take an azimuthal symmetry, an azimuthal average of the signal, and you can now have a one-dimensional set of wave vectors. And for each one of them, you can characterize these dynamics. And what you get is basically this black point that you see here in this plot. And you can compare this with the results you would obtain with a classical light scattering, dynamic light scattering setup. And you see that not only they agree very well, but also they explore different regimes. And the main motivation is that normally in dynamic light scattering, you go to large scattering angles because you have to be outside the transmitted beam, while in DDM, you go inside the transmitted beam and you have access to a very low wave vector regime. So now this works pretty well. So I guess that my time is practically over. Do I have still 3 minutes to show you at least a couple of applications, or we are really strict in time?
That's fine. It should be fine. Okay.
So the first thing I want to tell you is, of course, that as I promised, this does not only work in bright field. So in this work, these authors show that you can do bright field analysis or fluorescence analysis of the same particles and you get the same result. So tau of Q as a function of Q is basically coincident. And you could also compare the performances of this DDM with a very classical fluorescence technique, which is called fluorescence correlation spectroscopy, which is basically based on analyzing the number fluctuations of particles in a given volume. So you don't have Q-resolved information in this FCS. You have only one characteristic relaxation time. But from this, you can extract the diffusion coefficient. And you see that the results obtained with the two techniques are pretty much the same. You can also increase the size, the concentration of your colloids. And when they start interacting, you can basically compare the results of DDM with tracking, and you see that tracking at some point fails, even if the particles are large, and in principle you can track them because they are large enough. When they become too many, basically they superimpose in the microscope image and tracking becomes unreliable, but still DDM analysis work, which is this blue thing. And you can fit your data of the diffusion coefficient as a function of the concentration of your particles to models that allow you to tell something about the potential with which these particles interact. And in this particular case, this fit would be R-sphere and is not compatible with the data. And this fit is charged particles, which is compatible with the data. You can use it with particles that are B-dispersed. In this case, it's a mixture of particles that are 50 nanometer and 1 micron, and you can see both of them. And this has been used to be implemented in the International Space Station by Jacinta Corwin and collaborators. And you can measure systems in which some of the assumptions behind DDM are violated. For instance, in this case, the system is not exhibiting a stationary dynamics. The dynamics is slowly changing in time, which means that your analysis must be performed on chunks of the video on which you can assume that this time stationarity, at least in principle, holds. Similar results are obtained in this case, in which the colloidal particles are initially separated, then you put some magic, in this case it's temperature, you change the temperature, and the particle can now attract each other and form a colloidal aggregate. And in this case, DDM is used to study the relaxation time as a function of the wave vector. And you see that this is not any longer diffusive, exhibits a more complex dynamics, which is basically has 3 stages in which different physical processes dominate the dynamics. And I won't go into detail, but this is just to tell you that this is not a simple system in which you have diffusion. You have elastic propagation in the network and some other more complex relaxation phenomena. You can also study systems in which the particles not only translate, but also rotate. Of course, the particles need to rotate, but give rise to a signal which is proportional to the rotation. And this is not normally true for spheres in a normal experiment. You need to have special spheres, for instance, spheres in which there is an anisotropic, optical anisotropic core, or particles that are not sphere but are elongated, like, for instance, bacteria. And you can study systems made of two different particles that are fluorescently tagged with different fluorophores. So, for instance, large particles are red and small particles are green. And so you can study the dynamics of the two kinds of particles and also the correlation between the two. And you can find, for instance, specific regimes in which the ratio between the particle sizes give rise to very anomalous dynamics of the system. But I will skip a lot of things. I just want to mention a couple of examples that may be more interesting. You can see proteins, which are very small objects that cannot be individually resolved with a microscope. In this work, they have seen proteins in aggregates, but we have also unpublished data in which we have seen the monomers of the protein. So if you think about this result, you are seeing a single protein, so signal coming from a single protein, which is of the size of the order of nanometers, and you are doing that with a commercial microscope without laser or anything like that. So you can measure bacterial motion. The group of Wilson-Poon has done a lot of work in this respect, measure the velocity of the bacteria, the distribution of the velocity, the variance, the diffusion coefficient of the bacteria when they are dead, and so on and so on. One thing that I think could be interesting for some of you in the audience, you can use combination of confocal microscopy and differential interference contrast to measure different things in the embryo of the oocyte of Drosophila. And in particular, this allows you to compare the motility of actin and on this, which is this signal on the left versus the O-plasmic vesicles. And this is actually quite interesting because normally the vesicles can be tracked, but the actin cannot. And you can find that they move by a combination of diffusion and ballistic motion, and so on and so on. You can apply it to cell and many other things that due to my unforgivable slowness, I didn't have time to tell you too much in detail. So I hope I excited you enough for you to be willing to try and join the party. And I thank you very much for your attention and for your patience in this instance. Thank you.
Excellent. Thanks, Roberto. That was really excellent talk. Yeah, there's lots of people clapping in the audience. So yeah, don't know if we've got any questions from the online audience today.
I'm happy to kick it off with questions. So you mentioned that there's lots of different applications for this, and a lot of it depends on getting the right intermediate scattering function, right? So you've got a process, you need to know what the intermediate scattering function is so that you can fit parameters out of it. What's the sort of scope for being able to use this to actually determine what the intermediate scattering function is if you don't already know that? So to use it to probe dynamics rather than to fit parameters out of them.
Okay, so the point of, okay, let me put it in this way. So if you see something in real space, you see something in real space. And the main advantage is that you can characterize the motion. And I don't know, for instance, if you track particles, you can measure the mean square displacement. And when you have the mean square displacement, you can see if this mean square displacement or your probability distribution function for a displacement occurring at a given delta t is compatible with what you have in mind. Now, you still need a model, but your model has a very strong boundary, has very strong constraint, because it needs to fit with your observation in real space. And so when you look at particles moving in real space, for instance, in a straight line and then changing direction, well, you have a big help in defining a model, because you can say, okay, I will now, in my model, I will have to put in, from the very beginning, a directional motion that is persistent, and then some sort of random reorientation ingredient, which would force the particle or whatever I'm analyzing to move in a given direction. So this is the case, for instance, for bacteria. In bacteria, this is the so-called run and tumble motility. And of course, if you can track bacteria, you can more easily develop a model for them. But at the same time, and this is the main reason why I'm showing this slide, even in the absence of a model, if you take your intermediate scattering function, you could try to do the same thing in a different way. For instance, in this work, Poon and collaborators, what they did was to take the intermediate scattering function, and instead of plotting them as a function of tau, plotting them as a function of q tau or q squared tau. And what you see is when you plot them as a function of q tau, the first part of the decay collapses. And when you plot it as a function of q squared tau, the second part of the decay collapses. So this tells you that the first part is a ballistic process, and the second part is a diffusive process. Now, in trying to develop your model, you now have the same kind of hint that you would have from the tracking, but you need to be able to read it in a different way. So you will always be at a disadvantage in Fourier space, because of course you don't see things in real space so commonly, so frequently as you do you don't see things in Fourier space so commonly and so frequently as you do in direct space. But at the same time, the information must be the same. It's just that you have to find a way to get it out. So to close on this, or maybe to understand if I answer your question satisfactorily, if you don't have an intermediate scattering function, it's very difficult to be super quantitative, but you can still do a lot of things. For instance, this is one. Another one is in some cases, for instance, even we don't have a model. And what we do, for instance, is to take a characteristic time out of this curve without a fit. For instance, by taking the point at which the curve dropped by a factor 1/2. So this is very typical also in light scattering experiment. And it gives you an idea of the relaxation in your system, even when you don't have a model that works, which still can happen, right? So it still can happen that you have a model that, you don't have a model that fits your data 100%. But things can be made as complex as you want, because, for instance, these are the work by the same group. In this work, they also implemented, for instance, the helical motility of it's not the, how is called this? It's not a flagellum, it's a cilium, I would say, of the spermatozoa in the model, and they saw this as oscillations in the intermediate scattering function, and they could fit it in a very nice way. So you may find a good model after a long time. You have your data, but a good model is always available.
Yeah, that's great. Thank you.
Let me mention one other thing I think that can be useful to this. I don't have the data to show, but we recently published a paper in which we show, we analyze a system. Actually, it's exactly this system. Is exactly this system here. And we take the movies of these green particles and we analyze them with DDM. And so we find that this intermediate scattering function cannot be fitted to an exponential, but can be fitted to a Lorentzian. I'm still talking about Lorentzian in Q, in delta T, sorry. So, pardon me, a Lorentzian in Q. So basically 1/1 plus dq squared delta T. So this thing is compatible with a theoretical model of the so-called diffusing diffusivity motility. So the idea is the red particles are not static, they move, but they move more slowly, and they are a sort of glassy matrix for the green particles. So the green particles don't move freely, they explore a very glassy environment. Now this thing creates two time scales. There is a time scale which is the diffusion of the small particles, and the time scale over which the red particles move. So if you wait a very long time, and the red particles can move very much, you still recover a normal dynamics for the green particles. But if you don't, each particle moves in a different way, and this heterogeneous dynamics gives rise to the so-called Brownian yet non-Gaussian diffusion, in which you still have Brownian motion, but the probability distribution function for the particles is not a Gaussian. And because of this, your dynamics cannot be fitted with a normal exponential that you use in most of the DDM experiments. You need to use another function. This model has an exact solution only in Fourier space. If you try to bring it to real space, you don't have an analytical solution. So this is an example in which real space analysis will be less informative than Fourier space analysis. So you can also happen to have the opposite. So real space being less immediate and less modelable than, if you can use this word, I don't know if it's proper English, than Fourier space.
Thank you.
Thank you.
Katerina?
Yes, hello. Thank you for the great talk. We're working together with team on the DDM stuff. I'm not sure how much conversation you had with team. We are doing this advection, diffusion, and active streaming in the oocytes in the context of IVF. So I just wanted to ask, because you showed the case where you didn't have the exponential decay, and you said there are other dynamics going there, like the elastic propagation in the medium.
Yes.
So I'm just interested in like detecting from the diagrams the type of physical processes, because you said that there are other physical processes. I don't want to get into that, but it's very interesting to be able to see the diagram and just detect, oh, now I have diffusion. I don't have only diffusion, I have advection, I have other kinds of propagation and so on.
Okay, so in this particular case, which is the one I think you are referring to, we always fitted all our data to exponentials. The thing is that fitting with an exponential of time didn't work that much, unless, I mean, maybe here worked a little bit, but we needed to introduce a so-called stretching exponent. So it was not in the form e to the minus alpha t, but it was in the form e to the minus parenthesis alpha t to the power p.
Right, okay.
When this p is equal to 1, you get normal, let's say, exponential behavior. When this p is less than 1, you get a so-called stretched exponential behavior. So that's what we found in our experiment. So for instance, in this gel, at the beginning of the experiment, the particles are moving diffusively, and then they start aggregating. And you see that as soon as they aggregate, the dynamics becomes more stretched and more stretched and more stretched. At the same time, the prefactor of this stretched exponential relaxation, or this alpha I was mentioning in this thing, this depends on the mobility. So with p equal to 1, this will be the diffusion coefficient. But when p is not equal to 1, this is a sort of effective diffusion coefficient, but you can still get out the characteristic time. And so if you choose a q, I think in this case was here in the middle, and you characterize this characteristic time, you see that this characteristic time changes as a function of q, of delta t, sorry. So as the system ages, the dynamics become slower and slower and slower. Now, in all these cases, a stretched exponential was good enough to fit the data. But it does not mean that the dynamics is diffusive, because then you have to see how this time depends on Q. And the dependence on the time on Q can be linear in Q, and that would be ballistic, quadratic in Q, that would be diffusive, or can be, for instance, like in this case, Q to the minus 3, and that is something else. Depends on the fact that you're probing different volumes and the elasticity of the gel on different volumes. So, but in none of these cases, the relaxation was non-exponential. If you accept that we call exponential a stretched exponential, this was still exponential-like.
Right.
In the example I was making before, where there is a Fickian yet non-Gaussian motion, in that case, an exponential fit, even with a stretched exponential, was not better than the Lorentzian in fitting the data. The Lorentzian was way better.
Nice.
So I think that what I wanted to say, and I hope I didn't confuse you, is that most of the times we use models that give you a good estimate of the correlation time, because if you fit the data for this system with a stretched exponential, is not terrible, right? It works a little bit. But if you fit it with a Lorentzian, it's a way better fit.
Mm-hmm.
And we wouldn't have done that if we didn't know that there was this model for diffusing diffusivity, and the model was suggesting this particular form. So what I'm saying is that you can go back to the data that you acquired years before and maybe find a better model at a later stage.
Right.
But you have to look at both the scaling of tau with Q, so what we call the dispersion relation of the material, and also, for instance, in the case of a stretched exponential, is very informative how much this value changes. And the reason why I'm mentioning this is because a stretched exponential can be naively thought of a superposition of different exponentials.
Mm-hmm.
And so when this stretching exponent becomes smaller and smaller, you can think that your distribution from which you're drawing is getting larger and larger and larger. So this is an interpretation. Of course, in some experiments could be good, in some others could be BS. It's actually up to you to choose if in your experiment is good or not. But typically, for instance, if you have polydispersed particles, each one relaxing with an exponential decay, then it's not uncommon to see a stretched exponential as a result of the superposition of particles moving with a different diffusion coefficient.
Right. Okay.
Did I answer your question?
Yes. Yes. Thank you.
Thank you.
Okay, there's no more hands up, so I think that's time. So yeah, thanks again, Roberto, and yeah, I'm sure people can send you extra questions by email. But yeah, that was really nice, and
thank you.
Thanks everyone for attending, and also keeping out for the next season announcements for our future talks.
Thank you so much.
You all.
Okay.
Okay, bye for now.